Hi everyone. I hope many of you have heard about the big data but don't have an idea what exactly it is, right? So, if you are new to it and exploring big data for the very first time, like what big data is and its concepts, then this video is for you. This video is mainly for the beginners, anyone who is completely new to the big data. So, today's agenda basically is to cover the fundamentals of big data. What is big data? V's of big data, like distributed computing and distributed storage, vertical scaling, and horizontal scaling. Okay, everyone should know about big data first before moving into Hadoop and Spark, like big data frameworks. So, this is what we will be seeing today. So, let's start. Big data. What is big data? Big data is a collection of data that is huge in volume. So first and basic property is this one. When we say big data analysis, we are processing some data for business decision, right? So obviously it will be huge in volume because we are processing the historical data to get insights. And we are in the era of internet where it is easy to penetrate. Like even if you take the example how people can easily access the internet, right? Everyone are having smartphones, smart devices, using the internet, working on social media. So all those things are there. So at least here, as we grow in the era of internet, we know how rapidly and how exponentially the volume of data is also growing, right? And that is day by day means on daily basis. If you imagine a number combining the data from all the platforms, it could be social media, entertainment, e-commerce, or data getting generated from the smart devices which we are using or anything. So it could be in the petabytes or exabytes or something like that. So it is a data with so large size and complexity that none of traditional data management tools can store it or process it efficiently. So this is the most important thing you need to understand. Here, whenever we hear anything about the data, our first instinct is to think about databases, right? Most commonly used databases, which we already know probably in the software engineering or even anyone who belongs to CSE or IT, they might know it, right? Like there is a subject called database management systems where you usually read about this transactional databases or relational database management system, right? So since this data is very huge in volume, these databases, like traditional databases, cannot handle after certain threshold value because those databases have their own capabilities. They have their own storage capacity and scaling capacity. That is why. So you can say this is the most relative definition of big data. Now let's talk about its technical definition, because when you started working on a problem, you need to ask this question to yourself, like whether this problem is a particular big data problem to solve or not. Because in the industry, not every problem is a big data problem, right? So how to basically identify what are the key components of it and what is the actual technical definition uh, for the same. So here we see like the technical definition of big data actually revolves around the five V's, right? So majorly you hear from the people about three V's of big data. People who don't explore or who didn't explore other V's, they will say that big data is basically a terminology which follows three V's, right? So these three V's, which are in the first row, velocity, variety, and volume, these are the main three V's of the big data. Rest are, you can say, something which makes like a complete definition. Okay. So what are these five V's basically? Let's talk about it one by one. Velocity. So this refers to the speed at which new data is generated and The speed at which data moves around with the growth of the internet and smart devices, data is being generated continuously in real time from various sources. Means any problem statement like where the rate of this data is generated is the problem. Okay. So generating this data depends on, you can say, there is a term frequency, or you can say velocity is involved while generating the data. So this is all about the velocity part, right? So in general, if you are working on a problem statement, which probably lies under this velocity, in that problem statement, if data is getting generated with this frequency, so obviously big data definition is getting satisfied here, and we can process the historical data, right? So whenever we talk about the data analysis, you can have a historical data, which we probably call as a batch data processing. So good example for the batch data processing is your monthly bills. Let's say you are a bank. For example, you are providing the credit cards to the customers, right? So as a bank, what are you doing is every month, like every month end, you are generating the due bills to your customers. So this is like you're not processing the data on daily basis, right? So but at the end of the month you are generating those bills, and you're doing this kind of batch processing. Next is near real time. So near real time processing is like if there is an event which happens instantly, and the processing will start maybe after some lag. One example for near real time is like, for suppose you have posted something on Instagram platform, right? This platform has a variety of background processes that inspect your content for policy violations within a few minutes, right? As soon as you post, it will verify those. So here your content is posted in real time, but it is removed in near real time if an algorithm decides like you're violating the policies. So that's an example. And then coming to real time and streaming data process, here like real time and streams are basically same. Means as soon as the event is generated or action happened on source side, instantly we are capturing it and processing it. For example, you can take like transactions in bank. So as soon as you credit or debit your amount, your account is updated with the current balance, right? So that's all about velocity. Now, next is variety. So variety in big data refers to the different types of data that are now available, like what kind of data we are going to process. Here, like big data can include structured data, semi-structured data, unstructured data, and even complex structured data. So before this distributed computational logic, right? Before this distributed storage concepts and all, right here how we are interpreting the things, obviously no one was talking this much about big data, right? If you go back to 20, 30 years, obviously no one was talking about this much for the big data. But when we talk about it, when we started deep diving into big data, and nowadays data is something which is crucial, right? Even there is a phrase, big data is new oil of the industry. That is completely true. Like the kind of value you get from the raw oil in order to empower the industrial economy, in the same way, big data, data analytics is helping the information economy. Okay. Like without this, no company probably would be able to survive in the industry, because if you want to compete with your competitors, you always need to know where you are lacking and what best they are doing. And this is what you can know if you are analyzing your data properly. So earlier people were focused on structured data where you have something in Excel sheet, probably in row column form. So people were talking about that one, but now we know that all types of data is super important to analyze. And that is why you will see structured data to be processed, unstructured data, semi-structured data. So three types of data here is uh, let's quickly understand how our structured data, unstructured data, and semi-structured data actually looks like. Okay, so coming to structured data again, uh, you can probably compare it with the neat and clean data to be processed, right? Which will have some schema imposed to it. Schema as in column names, so that you can identify what value this particular column holds, right? And it will be a sort of number of rows and number of columns, proper tabular structure. So this is easily understandable and we can process it. So this kind of data comes under our structured path. Okay, so whenever we talk about data analytics at the end, after doing all the data cleaning by data engineers and providing the transformed data, so this is probably the end goal, right? When it comes to data analytics, to have a transformed data in such a way so that we can use it and process it in the commonly used data warehousing services like Hive, Redshift, Snowflake, okay? Another thing in unstructured data, usually you will see the use cases, mostly in data science related projects, okay? And not just data science, that is one example, okay? So nowadays what we can say, the audio recording, video recording, images, those are data as well, right? So as a human being, you can visually see those things and probably listen to it, but if you decode it, like how it is getting stored in the memory, and if you want to process it, then that is not doable because we cannot understand how it is. So we cannot understand the data. That's why it is unstructured. You cannot know how this data looks behind the scenes, okay? So unstructured data is all about that. Like, for example, you can take an example for this as face mask detection projects, right? Or the image recognition related data science projects. So those are typically dependent on these unstructured data where, like, if you talk about facial expressions, so if somebody wants to predict based on the face, the expression, right, like the smile face, the sad face, so here they are processing this unstructured data and writing the algorithm on top of it. So this is how the unstructured data works. You can apply this to text as well, like any textual book or PDF. You are writing script for web scraping where only the textual data you are pulling into the system and trying to process it, right? So because that textual data will not have any kind of schema or any simple kind of tabular structure to be processed, so this is unstructured data. Okay, last one will be semi-structured data. Semi-structured data is how you basically understand it, like it is flexible in the first place. It is not in the typical structured form, or it is not in pure in the unstructured form, right? But in between sort of file format. Like flexible means we can add the columns or delete the columns as well, right? And there is no strict schema imposed here. And again, if we want to process it, we need to work on it and we need to convert it in a proper structure to be processed. So these are the examples of semi-structured data. So usually the data you see in the XML file and similarly in JSON data as well, these will be coming under the semi-structured data. Okay. That's all about types of data. Next, we go to volume. Talking about volume, I guess this is very prime definition of the big data problem. I mean, like there should be a significant amount of data which is there to be processed, and then we will call it as a big data problem, right? And usually it will be in hundreds of GBs or in terabytes or petabytes. So this is about the volume part. Like example of high volume data set would be all credit card transactions on a day within USA or Europe, something like that. So that's all about volume. And talking about other two V's, veracity and value. So veracity is all about how valuable, as in how much you can trust this data, okay? Or cleanliness of that data, because if you have some sources to generate the data, it's not like every time you're receiving full-fledged proper data to be used, okay? So in order to get any meaningful information out of the data, you should first know that whether you can trust this data or not, or this is completely useless. And having so much anomalies and having too much of garbage to be processed, right? uh, Obviously in that case that type of data is not going to be used for anything, so we can discard that. Next is value. If you have the data, you should understand whether like if you start processing this data, it will make some sense or not. At the end, you will be able to get some values out of this data or not, okay? Like, so probably this is how you can understand it. For example, if you have a data set with only names, say you have a list of people watching this video, what value you can get out of these names? What can we do with this data, right? So if there is some numerical value, like there is some something attached with this human names, in that case I'll be able to bring out some value from that data. Like now let's say if you have name, age, gender, location, we can do some analysis based on this data, like which age range is mostly watching this video and all, right? So then this data makes some sense. By analyzing and categorizing the data, we can get some meaningful information here, right? So after evaluating all these five V's, you can say that this is a big data problem to be solved. So this is the complete technical definition of the big data. So examples, right, very common. Nowadays, this is something common everywhere. As I said, if you want to survive as an organization in the current industry and you are not utilizing the data you have, probably within few months, your competitor will acquire your market. And this is the reason in every domain you see big data engineer, data scientist, and data analysts, because this data analytics component is tightly coupled with the data domain, right? And different data domains basically. So whether you talk about the social media platforms, they need the data professionals to work on these data engineering related complexities, solving data mysteries as a data scientist, data representation as a data analyst. So example like how we are processing the big data on social media, like whatever you see in terms of posts, likes, share, their analytics is all about data processing there, right? And customized ads is the best example you can take. Like on Facebook and YouTube, you'll be getting the customized ads, right? So coming to healthcare, like I think this is the domain which has improved a lot just because of the production of this big data. So that can be used to even identify some critical diseases and their cure, right? And coming to finance, I think finance as well, like for financial prediction, the good example is stock exchange and fraud detection. right? The good example in the banking and finance domain, how big data and data analytics can be used here. Yes. So coming to telecommunication, call detailed records and their processing is the example for it. And e-commerce, again the examples like recommendation engines, right? And how recommendation engine is working is it is analyzing the user activity basically, and what kind of products you are actually buying frequently. So what are, so that's what you get, customized recommendations. Okay. So IoT is nowadays smart devices like mobile and all, they are also generating a lot of data which can be processed in real time, right? So transport is ride daily services like Uber and all. So these dynamic and analyzing customer behavior, all those things comes under this part. So in all these domains, you can see the critical use of big data and data analytics. Hmm? So far, what we talked about is just touching upon the big data definitions and basic terminologies of it. So now we are moving to big data processing, like basic terminologies of it. Before we move to data processing frameworks and its architecture, so let's talk about few technical terms which you will be keep on using in your day-to-day job as well as when understanding or explaining this architectures. Okay, so I will touch upon those few basic technical terms so that you know it beforehand when we talk about the architectures of any computation engines. So first, let's try to understand the clusters. So let's take the simple example. Okay, let's say I'm having my laptop and my laptop will be having a capacity, right? That's why we want to purchase systems like decent configuration. uh, we want to purchase systems with decent configuration. So one single machine basically, right? One single machine is capable enough to store the data and process as well, right? So when we talk about in terms of hardware, like so any machine, right, it will have majorly two components: the memory to store the data and processor to process the data. Okay, so the single machine will be having this kind of limitation. Now if I say that you need to process 3 terabytes of data, 3 TB of data, so you would be able to do that with the help of your laptop or desktop machine you have. So the processing of 3 to 4 TB of data, terabytes of data, absolutely no, right? Because even if you imagine, right, your hard disk is somewhere around 520 GB or something. Like you will not even able to dump that 3 terabytes of data in your system, right? If you are not able to do that, how we are going to process it, right? And now when we talk about the big data, we are talking about hundred of GBs and terabytes, right? Hundreds of GBs and terabytes of data to be processed, right? So how it will happen? So that was the reason where these components or terms distributed storage and distributed computing came to use. Here, with one single machine, you will be having limitation, right? So you cannot store that terabyte of data into one system. So what if we are able to divide the data in some segments, and instead of storing that entire 3 TB of data in one single machine, Let's divide it and store it in different machines. Like I will buy probably 10 laptops and I will divide the 3 terabytes of data and put some segment into different laptops. Okay, so in layman terms, this is the example of distributed storage, you can say. You broke the entire data. You have different hardwares, or you can say commodity hardwares or machines with you, and you stored that broke component of data. So you have split the data and stored it in individual machines separately, right? So distributed computation, right now your 3 TB of data, like your 3 terabytes of data, you have broken it into multiple parts, right? And this multi-part data is actually available in various machines, right? So absolutely, in order to process them, like again, you cannot bring together at one single machine and process it there, this all data. So you need to do this processing individually on those machines, like where you have stored that broken data. Hmm? Because those machines will be processing that specific amount of data which you have stored there, and whatever output will be generated by all of those machines at the end, it needs to be combined, right? So this is the example of distributed computation in layman terms, you can say. So in order to achieve it, we need a sustainable infrastructure. Like in order to do this kind of big data processing and even to store this terabyte or petabyte of data on scale, we need a sustainable infrastructure. That is what we call a cluster basically. Like you can say cluster is basically a combination of the commodity hardwares, like commodity hardwares means of those machines which we have, like some which we have some computational power and storage capacity as well, right? um, so when you have the infrastructure where more than one machines are connected together, you can call it basically as cluster. Okay, sometimes you will also hear this term node. Whenever you use the term cluster, you use this term called node. So these commodity hardwares, like which will do this distributed storage and processing, those are known as node. Okay, so moving on to the next part. This part is also very much important to understand, right? Because in the beginning, when we saw, what we saw is the huge volume of data which cannot be handled by the traditional databases. Okay, so why these two terminologies are important to know? The difference is vertical scaling and horizontal scaling is vertical scaling is also known as scaling up. Okay, meaning that if you have a machine, right, and if you are trying to increase its capacity, that is known as vertical scaling. Here you cannot increase the capacity after some threshold value as the server has its limits, right? And coming to horizontal scaling, it is completely opposite. Like uh, that is the reason you will keep on hearing this term mainly. So that horizontal scaling, you'll be keep on hearing this term, which is opposite to vertical scaling, right? So even in the design rounds in interviews, your interviewer will ask you, please design a scalable solution. So your application should be horizontally scalable. So these are the terms which you'll keep on hearing. What we mean from the horizontal scaling is like you have a machine. Nowadays these commodity hardwares are cheap. Okay, we have a cloud, we and the infrastructure on cloud is also cheap as compared to on premises infrastructure. Okay, so that is the reason horizontal scalability is about having the machines of same configuration or lighter configuration, probably 8 GB RAM and few GB of external disk. And what we will do as per the data volume or as per the load, right? So let's say you started your new platform, right? And probably on day one you can say only 100 users subscribed your YouTube channel or something. So at this moment, the data volume is definitely very less. So, uh, so you can say the data volume is definitely very less on the platform. But as soon as you go viral, like obviously, more and more people will join your platform, right? And the load increases on your platform. And when the load is increasing, your infrastructure and applications should be capable enough to handle that load on scale, like seamlessly, without breaking, without any failure. Okay. So, and how would that be possible? If your application is horizontally scalable, means whenever there is a huge volume of the traffic, like instantly, what should be done is automatically more and more servers should get added in my application, and the load must be distributed properly, right? And that is the reason where we talk about clusters, right? When we are dealing with 100 customers, today I feel that only 10 node of cluster would be fine to process this much of data. But after 1 month, if we started handling thousands of users, then obviously I need to scale my system, and for that I will add more and more nodes here. Let's say I will add 50 more nodes. What we did here is, instead of increasing the capacity of one particular node, we just added more and more machines of same configurations into it. So this is all about horizontal scaling. Hope you have understood what is big data and all the terms you use while working with big data. Thank you for watching. Please subscribe to my channel. Thank you.